All right, so the goal of Chapter 2, Section 2, Limits Involving Infinity, is to understand when limits equal infinity and to understand when limits approach infinity. So we have two types of infinite limits we're going to look at. We're going to look at when a limit is equal to infinity, and we're also going to look at when a limit is approaching an infinity. So yesterday we talked about the squeeze theorem. The squeeze theorem is essentially an analytic approach to understanding what happens when we smush a function in between two other functions. So we have h, f, and g, and we're going to look at what happens when you squeeze f in between h and g. We use this theorem a lot to talk about trigonometric functions, and another part of section 2 is looking at trig functions. So there are special trigonometric limits. We talked about these yesterday. We talked about the limit as x approaches 0 of sine x over x equaling 1. And we also determined that the converse of that was also equal to 1. So basically you could flip the limit as x approaches 0 and you got x over sine x was also equal to 1. The one we haven't talked about yet is special trig limit number 2, which says the limit as x approaches 0 of 1 minus cosine x is also equal to 0. These are just two limits you're gonna have to memorize. There's no easy way about them. You just need to know them. If you like to know where something comes from, then down here at the bottom is the proof of where they came from. And this proves to you why each is equal to what they're equal to. But again, that's like extra reading if you like or need to know where something comes from. So we can look at something like the limit as x approaches 0 of tan x over x. Obviously, if you plug in 0, the tangent of 0 becomes 0 over x. So once again, when we get a limit and we get 0 over 0, the rule of thumb is to simplify it algebraically. So we're going to rewrite tangent for what it is. Sine over cosine. And we know we can't have a fraction in a fraction. So we're going to get rid of that denominator fraction. And we get the limit as x approaches 0 of sine x over cosine x times x. And what we should notice is we get sine x over x as part of that limit. Well, the properties of limits say a limit can be rewritten. So you could rewrite this as the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. So that your first limit is equal to 1. The cosine of 0 is 1. So you get 1 times 1, or 1. So we did something similar to this yesterday. You have sine 4x over x. Well, we're missing a 4. So we're going to multiply the top and bottom by 4 over 4. So this becomes the limit as x approaches 0 of 4 sine 4x over 4x. As long as the coefficient of the inside x matches the denominator's coefficient on x, then the limit as x approaches 0 of that sine 4x over 4x follows our rule and becomes 1. I shouldn't write it like that. So really, this is like saying the limit as x approaches 0 of 4 times the limit as x approaches 0 of sine 4x over 4x. So you get 4 times 1, which is 4. Remember, the limit as x approaches any number of a constant is always the constant. That was the very first limit property we learned. One minus cosine squared x should look really familiar to you. 1 minus cosine squared x should look familiar to do. It is a special trig problem, not special trig problem, special algebra problem again. Anytime you have a perfect square minus another perfect square, we think difference of squares. So the minute I see that 1 minus cosine squared, I am rewriting my problem as 1 minus cosine x, 1 plus cosine x, all over x. We see that that is a special formula. It's the 1 minus cosine x over x. Well, that special formula says the limit as x approaches 0 of that is 0. So really, the minute you get 0 times something, does it matter what the other limit's equal to? No. So even though it's equal to 2, 0 times 2 is 0. So we have h of x equals negative x squared, f of x equals x squared, cosine 10 pi x, and g of x equals x squared. Use the limit of x approaching 0 of f of x with the squeeze theorem to show that it's equal to 0. So again, we can see that f of x incorporates the x squared. So we can start by saying that the limit as x approaches 0 of h of x is equal to negative 0 squared, which is 0. We can say that the limit as x approaches 0 of g of x is equal to 0 squared, or 0. And then we can say that the limit as x approaches 0 of f of x is equal to the limit as x approaches 0 of x squared cosine 10 pi x. And then you can say by the squeeze theorem, since the range of cosine 10 pi x is -1 to 1. So by the squeeze theorem, since the range of cosine 10 pi x is -1 to 1, and the limits of the outer function x squared are equal to 0, then the limit as x approaches 0 of f of x is also equal to 0. So I say it all the time, calculus is different from any other math class you've ever taken, because in calculus, we write sentences. In calculus, we write sentences. They're going to tell you the answer all the time. They want to know why you get that for an answer. They're telling you that the limit is equal to 0. They want to know if you know why the limit is equal to 0. Calculus isn't about finding the answer. It's about explaining how you get that answer and understanding the answer. So yesterday we did a lot of graphing and sketching. I'm not sure we need to waste time kind of today. All of these are going to look very similar to this idea here. If you really want to know what it looks like, you can graph it. That ultimately leads us into looking at horizontal asymptotes. Because just like the squeeze theorem squeezes to 0 at that one point, we have horizontal asymptotes, which are constantly approaching or getting near a 0. So it says, does the function 1 over x have a horizontal asymptote? If so, what is its equation? So think about the graph of 1 over x. We know that x cannot equal 0. So we know it has a vertical asymptote at x equals 0. If x is negative, then y is negative. Because if you plug in a negative for x, you're going to get a negative. So that means that this part of the graph is always negative. And if I plug in a positive, then it's always positive. Now I know my graphs are going to infinities, because if you think about something like 1 divided by 0.000001, anytime you divide a number by something really, really small, so like 1 divided by 0.000001, 0, 0, 1, you're going to get something really, 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 really big. Because really that 0.001 is a fraction within a fraction. And that fraction is really kind of like saying 1 over 1,000 or whatever. So when you flip it, you end up getting 1 million. So 1 over something really small is really big. 1 over something really small is really big. That's how we say 1 over 0 is approaching infinity. So if you take a limit as x approaches a number and you get 1 over 0, that limit is going towards an infinity. Now, that's a little sidebar to end behavior that we're going to look at tomorrow, Monday, I guess. Back to asymptotes. Does this have a horizontal asymptote? Is my graph not approaching 0 on y on both ends, but never getting there? So the answer is yes. 1 over x has a horizontal asymptote at y equals 0. So this chart sums up all the different horizontal asymptotes and how they can occur. If the denominator is greater than the numerator by 1, the asymptote is at 0. If their degrees are the same, it's the coefficient. If the numerator is greater than the denominator by 1, it's a slant. And if the numerator is greater than the denominator by anything more than 1, there is none. We describe asymptotes by writing them as y equal b equations. Asymptotes are y equal b equations. Asymptotes are found by going out on the infinities of x. So the limit as x approaches infinity equal to b, or x approaches negative infinity equal to b, finds a horizontal asymptote. So it says find the limit as x approaches infinity of f of x and negative infinity for f of x given the function x over square root x squared plus 1. So if the variables are the same degree, then it is the coefficients. So if you think about this, this has a degree of 1. The square root of x squared also has a degree of 1. Therefore, the limit as x approaches infinity is equal to 1. Because the top is getting really, really big and the bottom is getting really, really big. Now, when you take the square root of x squared, you have to consider that it's like an absolute value or that it's a positive and a negative. So the limit as x is getting really, really big negatively means that the top is a negative one, but the bottom is a positive. So we get -1. So what that means is the graph is increasing rapidly towards 1 and decreasing rapidly towards -1 on the opposing side. If you were to graph this, you would be able to see that. If you graphed it on your calculator, it would look like this. Where this is 1 and this is -1. And that idea of the split comes from the square root of the x squared. Okay, the limit as x approaches infinity of sine x over x. This is now an infinity. It's not our special trig formula. It's not 0. It's infinity. It's sometimes easy to think about this as 1 over x times the sine of x. So we know that the degree of the denominator and the degree of the numerator are not the same because we can't really discuss the degree of the numerator for a sine. What we can do, though, is think about the range of sine as going from -1 to 1. So in a normal sine of x graph, the range is -1 to 1, and it looks like, the continuous repeated curve in both directions like this. Now, dividing that by 1 over x is going to alter its look. It means that as x gets bigger, it's going to get smaller because it's getting infinitely and infinitely smaller. This is actually a mini squeeze theorem because we can say the limit as x approaches infinity of -1 over x should be less than or equal to the limit as x approaches infinity of 1 over x sine x should be less than or equal to the limit as x approaches infinity of 1 over x, coming again from the idea of that range of sine. So if you have the limit as x approaches infinity of -1 over x, we just looked at its graph. So 1 over x, we know, is going to look like the vertical asymptote at 0 and have a horizontal asymptote at 0. So as x is getting really, really, really big on the negative side, then we know that this is going to be approaching 0. Because 1 over something really, really, really big is really small. 1 over something really, really, really big is really small. So the limit as x approaches infinity of 1 over sine x has to live in the middle of those two limits. Therefore, by my sandwich theorem, it equals 0. Which really just tells me that this graph has a horizontal asymptote at y equals 0. If the limit of something is equal to 0, then you have a horizontal asymptote at 0. Similar type of problem, right? We have the limit as x approaches infinity of 5x plus sine x over x. So it's helpful to know those limit laws that say I can take a fraction and break it into two parts. It's really the same. This is really the same as saying 5x plus sine x over x. We're just adding like fractions, or, having that common denominator where we can add them. So you can take the reverse of it and split them. We just determined that the limit as x approaches infinity on the previous slide over x was equal to what? We just determined that this is equal to 0. What's 5 divided by 5? Or, sorry, I wrote 5 divided by 5. That should have been 5 over x. Sorry, I wrote it correct here. I wrote it wrong there. So not 5 divided by 5, it's x divided by x. So x over x becomes 1 plus heal. Say if the limit as x approaches infinity of 5. If you have a graph of a line that's the constant 5, as you go out on infinity to x, what's this approaching as x is getting big? As x is getting big, y is staying what? 5. As x is, remember, x gets big this way. As x is getting big or going to infinity, y doesn't change, it's 5. So this becomes 0 plus 5, or 5. If you need to go back or reference or look anything up because you're struggling between now and Monday, I would highly suggest looking at end behaviors of graphs, because this x approaching infinity, this is end behavior. This is what you would have talked about in pre-calc called end behavior. Okay, the vertical asymptotes are similar to horizontal asymptotes and that they are a line on our graph that does not exist in our domain. So the line x equals a is the vertical asymptote of the graph for y equals f of x if the limit as x approaches a of f of x is equal to positive or negative infinity. So what this means is exactly what happened in that example at the beginning. When I graphed 1 over x, we said that x equals 0 was a vertical asymptote because we know that 1 over x has x in the denominator, and the vertical asymptotes come from setting the denominator equal to 0. Yesterday, we talked about the limit as x approaches a number from the right and the limit as x approaches a number from the left. So in this case, if you look at the limit as x approaches 0 from the left, so that's approaching this way, where's my graph going? Well, it's going down and 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 down. So the limit as x approaches 0 from the left is negative infinity. As x approaches 0 from the right, the graph is going up and 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 up. So the limit as x approaches 0 from the right is positive infinity. If the limit as x approaches a number, whether it's from the right, the left, or just the number in general, is equal to an infinity, that tells us we have a vertical asymptote. That's what that statement is saying. If you get a limit at a number equal to infinity, you have a vertical asymptote. We find vertical asymptotes by setting denominators equal to 0. These are the points that it is undefined in the domain. Where graphs have vertical asymptotes, the functions have an infinite limit, as we just saw. So what are the vertical asymptotes of this function? The vertical asymptotes occur by setting the denominator equal to 0. So there is a vertical asymptote at x equals 3. Describe the behavior to the left and right of the asymptote. That is asking me to find the left and right hand limits. To find the value of the limit to the left of 3, think about on your number line, here's 3. What's to the left of it? Like 2.5 or 2.9. So if you look at 2.5 or 2.9, all we're going to do is quickly plug them in. 2 times 2.9, is that going to be positive or negative? A positive times a positive is a positive. So the top part of the fraction is positive. 2.9 minus 3. Is that going to be positive or negative? Negative. Positive divided by a negative is a negative. We know that the limit's an infinity because we know there's a vertical asymptote. I'm only plugging in that 2.9 to determine if my infinity is positive or negative. If I know there is a vertical asymptote, I know the limit is infinity. If I know there's a vertical asymptote, I know the limit is infinity. It is just determining whether it is positive or negative. So we're going to do something similar, but to the right of 3. So that's like plugging in 3.1. So 2 times 3.1 is positive. 3.1 minus 3 is positive. A positive divided by a positive is positive. You have now just acquired the skill to determine what's happening on this graph at 3. So you know there's a vertical asymptote, so you knew how to draw that line that's dashed. What you struggled with was whether those lines were going up or down. Well, now I know that to the left, my line is going down, and to the right, my line is going up. We also can quickly look at f of x and determine there's a horizontal asymptote where. The top is x, the bottom's x. So you have a horizontal asymptote at what value? Because the degree of the top and the degree of the bottom are the same. Therefore, it's their coefficients. So the coefficient on top is 2, on bottom is 1. Therefore, it's 2. So what that means, if there's a horizontal asymptote at 2, the limit as x approaches infinity of f of x is equal to 2. And the limit as x approaches negative infinity of f of x is equal to 2. So we've now found limits going to infinities and limits equaling infinities. Last one for the day, I promise. Find the vertical asymptote of f of x equals tangent x. Anytime you have a tangent, the first thought you get needs to be to rewrite it as sine and cosine. Anytime you see a tangent, your first thought is to rewrite it as sine and cosine. Because instantly now, I can see that this is a fraction. If I see that it is a fraction, then I know that there are vertical asymptotes at the cosine of x, the denominator, equaling 0. This is why we took the unit circle test. You need to know very quickly what x values the cosine of x equals 0 at. So I need to know that when I plug in pi halves, cosine is 0. I need to know that at 3 pi halves, the cosine is 0. And I need to know that if I add pi or subtract pi to that number, it's equal to 0. So this function, and think about the tangent, please think about the graph of tangent. So what this tells me is that the tangent of x has an infinite number of vertical asymptotes at x equals pi halves plus or minus pi k. So we're going to call a equal to pi halves plus pi k. Because k could be an integer if k is an integer. And if it's an integer, that means it could make k positive or negative. So what that does is that allows me to determine the limit as x approaches a from the right and the limit as x approaches a from the left of tangent, because the infinite vertical asymptotes are going to be the same to the left and right of a every single time. So if you're talking about pi halves, to the left of pi halves, all trig functions are positive. To the left of pi halves, all trig functions are positive because you're in quadrant 1. So that means the limit as x approaches a from the left is going to be a positive sign over a positive cosine, which means it's going to positive infinity. In quadrant 2, sine is positive, but cosine is negative because all students take calc, which means the tangent is negative, which means the limit as x approaches a from the right is negative infinity. If you graph tangent, don't have a lot of space on here. We know there are vertical asymptotes at all the pi halves. It means that here's pi halves. To the left of pi halves, it's going to be a positive infinity. And to the right, it's at negative. So this is to the right, it's at negative. This is to the left, it's at positive. And that behavior is going to repeat infinitely like tangent does. And if you put tangent x on your graphing calculator, you would be able to see that a little bit more clearly than my drawing over here in a corner, which I ran out of room for. Okay, homework's posted on Fusion, so you can use that and go from there.